we'll start with the next talk, and that's going to be Lucía Aballe. So Lucía, I have the pleasure also to know her since I came back from New York, actually. So I worked closely to her, and it's been a great pleasure. So we worked on spin dynamics and basically on how to image it in synchrotron. So I think today she will talk about synchrotron and how to measure things in Spintronics. And I think this is something very interesting and that we all have to take into account. And this is very important for the course. So Lucía got a degree in physics at the University Autónoma of Madrid. And then she did a PhD in Berlin at the Freie Universität, and a long postdoc in Elytra. And then she got the group leader in 2006 in the ALBA synchrotron, in the Circe beamline. So I think she's one of the best persons to talk about that. So my pleasure to have her here. So good afternoon, Lucía, and
good afternoon.
All yours.
I have my mic on, right?
Yeah.
I will put a timer, but in case I don't look at it, please let me know if I'm talking too much, okay?
I will, okay.
Okay, so welcome everyone. Good morning, good afternoon, good evening, whatever it is. Thanks for staying until the end. For some of you, I know it's very late, like it is for me. And let's start. My talk will be actually quite simpler than the previous ones. I will show mostly pictures. I know everybody's tired by now. And let's go ahead. So I am from ALBA Synchrotron, which is in Barcelona, so in Spain, but there are many synchrotrons around the world where you can go to do your experiments if you so wish. So a synchrotron is basically a big expensive lamp of X-rays of specific characteristics. We like X-rays because they interact very strongly with matter. And in particular for this talk, they interact very strongly with electrons. So of all the different processes that can happen when a photon interacts with matter, which is either ignore it, just no interaction, get transmitted, or it can just be diffracted a little bit, so deviated a little bit. It can be fully absorbed and all the energy transmitted to the material system, and then relax in the form of emission of photoelectrons or another transition and emission of other photons and so on. So all these things, when you want to measure, you have to think that these processes happen simultaneously. Although you are only looking at one or the other, depending on the technique you choose, they are all happening at the same time. So you have to choose what is best for what you want to ask. In particular, X-rays produced at synchrotrons go typically with energies from a few electron volts to a few tens of thousands of electron volts. So we would call the low energy ones up to 2,000 or 3,000 electron volt soft X-rays, and from there up hard X-rays. And as you see here, the cross-section of the different processes depend not on the element we are looking at, on which material we are looking at, depend also on the photon energy, and in fact they also depend on which core level, on which atomic electronic level we are looking at. And this is something we have to profit also. And as you see in this graph, which is unfortunately cut at 1000 eV on the lower side, but the inelastic processes, so absorption of the photons and emission of electrons and other photons with lower energy, is the predominant process in the lower photon energies. So from few thousand to a few hundred, let's say, which is what we will target mostly at synchrotrons. So as I said, the X-rays emitted in a synchrotron are special with respect to other X-ray sources. First, because the synchrotrons are very brilliant, which means there are a lot of photons per area and per time, but also per solid angle. So sort of a collimated source, let's say, or a coherent source, and more with newer generation of machines, which are now coming up. One can tune the wavelength, so one can choose at which energy to work in a certain range, and depending on the beamline one builds, on the apparatus one chooses, and builds, one can choose the wavelength. One can choose the polarization also with the help of so-called insertion devices, which are arrays, typically arrays of magnets that can make the electrons that are around the ring do funny little spirals or helices and so on. And then one can choose to have either horizontal, vertical, right-handed circular or left-handed circular polarization at will. And this is very important to interact with, to probe material properties that depend on orientation, like magnetization. No? And also, synchrotrons have a pulsed time structure. So typically, 500 megahertz. So typically every 2 nanoseconds, there is one pulse of electrons in the ring, and thus one pulse of photons in the beamlines. And the width of this pulse is of some tenths of picoseconds. So even without very sophisticated equipment, one gets, let's say, for free, this quite high temporal resolution of a few tenths of picoseconds, which can go even down to a few hundred femtosecond in so-called free electron lasers that I will not go into, but it's like the next generation after the synchrotron. So let me dwell a little bit on some of these characteristics. The fact that we have a tunable wavelength means that when we probe a magnetic material with synchrotron X-rays, we are doing it in an element selective way. So we can look specifically at the magnetization of this or this element. Okay, you see here the absorption spectrum of several 3D metals, and you can see that each one has its own energy. So I can ask specifically, nickel, what is your magnetization? Cobalt, what is your magnetization? Are you both parallel or anti-parallel? And so on. Do you have the same dynamics or not? Not only different elements, but in some favorable cases, one can look even at different, for example, oxidation states, or in the case that I will show here, one can look at different cations within a complex oxide structure. They have, each one has the particular peak, and one can look at the magnetization of each one of those, let's say, subspecies, no? Or cation sites. And this is just a little example, not to make the talk so boring, which is images of a magnetite surface. This is a spectrum of magnetite. As we go through the different dichroic peaks, 1, 2, 3, you will see the magnetization invert and then change and then go on. This is the so-called L2, L3 and L2 absorption edges, and each one has the characteristic dichroic signal that I think Adriana introduced the other day a little bit. The dichroism is just the, I will introduce it now, I think. Yes. From all the absorption by an element, there is some part, there is a percentage that depends on the relative orientation of the magnetization in the material and the incidence of the X-rays. Okay, so with circular polarization, we probe typically ferromagnets, and with linear, we probe antiferromagnets. So this is important also for what I will explain later. So what we are probing is only the part of the magnetization that is that has a component along the beam incidence. And this is a very famous historic picture by now, which shows in a multi-layer, well, in a B layer, let's say, of ferrite and a metal layer. One is an oxide, which is antiferromagnetic, and one is a metal, which is ferromagnetic. And by combining circular and linear dichroism at the absorption edges of both elements, it was shown for the first time that there is a correlation between the domain sizes and shapes in both, so that one is driving the other. Okay, this is a very famous paper by now in PIM. This in particular is PIM. I will go into the different ways to do microscopy in a moment. And finally, a note about this pulse nature of synchrotron radiation. What I show here, for example, is the temporal structure at ALBA, which is quite good. Let's say the pulses are quite narrow. They are only 20 picoseconds with all the jitter and so maybe 30, but very good. And as you can imagine, with a single pulse, normally we don't have enough signal to make an image. So what we have to do is repeat the process many times in a stroboscopic way with a very good timing and no drifting, so no jitter, to accumulate enough statistics. This has an important consequence. This is this type of measuring scheme where we excite with some whatever, I'm not saying what, we excite the system somehow. It can be electric pulse, can be a laser pulse, it can be whatever you want, can be a wave, and the system has a certain response time. It goes through certain changes, and by varying the delay between the pump and the time where our synchrotron pulse arrives, which is the probe, then we can do slices at the different timings, at the different delays. What happens that these can only be used to measure repeatable processes. So things that happen the same all the time. It is not applicable to measure emergent collective complex behavior and these kind of things. For this, we are still going towards the single pulse experiments, which is very hard, but it will come. There are, in certain conditions, it can be done. And this is just a very recent example from a spin waves emission from a vortex. The vortex is this little thing in the yellow. This was done at the Swiss light source at the Pollux beamline. And here you can see the time. This was excited about 1 gigahertz. And you can see this is the type of little movies that one can obtain and see, for example, the emission, propagation, scattering by the edges of the dot or whatever, interference of different waves and so on. This is just an example. Very recent one. Sorry, I didn't put the reference, but it's, I believe it's from 2020 and it's from Pollux. Okay, so a little bit more from the experimental side. As I said, there are many processes that happen at the same time, and we can choose what we look at. We can look at, for example, as the doctors do at the radiography, how many X-rays are transmitted. We can look at how many X-rays are transmitted after a phase shift. We can look at how many electrons are emitted from the sample as a consequence of the photoelectric effect, so detecting electrons. We can look at X-rays that are emitted by means of fluorescence, so that don't necessarily have the same direction or energy as the primary photons. We can measure the induced photocurrent, although it's a bit tricky because they are femtoamperes if we have a really small beam, but it has been done, and so on. So, and whichever one we choose, by the fact that we are using synchrotron X-rays that we can scan across different absorption edges and where we can tune the polarization, we have at the same time this elemental chemical magnetic contrast, okay, whichever approach we use. There are two basic experimental approaches that we can use, which is scanning or full field. In scanning, what one does is just focus the X-rays to a very, very small spot, a few tens of nanometer spot, and then the sample is scanned around this spot. Normally is the sample, not always, but normally is the sample. It's easier to scan the sample, okay? And then one can detect, as I said, either the transmitted X-rays or one can add other detectors. So you see this is versatile in this sense. We can detect, in fact, at the same time, how many photons are transmitted, how many are emitted by fluorescence, how many electrons are photoemitted, and so on. Whereas in full field, we illuminate a relatively large area, meaning micron size, 10 micron, 50 micron, maybe 100 micron. So still we need a lot of photons to have a good image. And then we have to form the image with some sort of lenses. Which sort of lenses? Well, depends a lot. If we want to look at transmission, we need X-ray lenses. if we want to look at photo emission, we need electron lenses. So these are two very different approaches that are highly complementary, and both are available at ALBA and in many other synchrotrons. And I will go through this, let's say, three approaches more or less thoroughly, let's say. How one can focus X-rays? Well, it's possible. It's not cheap and it's not in a small space, but it's possible. Okay, to start with, one needs a small source because the brilliance is at best conserved. We will not never be better than our source is. This is why there is a big effort worldwide to improve and decrease the emittance of synchrotron light sources. There is now ESRF has gone through a major upgrade, and upcoming are upgrades of, well, basically every synchrotron in Europe and otherwise. SLS2, ALBA 2 will come in 10 years. Well, everybody's doing BC2, everybody's doing the upgrade to the new generation. So what do we need for microscopy? Again, so what I just said, a small source. We need high flux because we are not going to probe a lot of material. So sometimes we do microscopy just because what we need to probe is a very, very small sample. Sometimes that's just the reason. And then we need the focusing X-ray optics that can be divided into main categories: reflective or diffractive, transmittive, let's say. Reflective, the most popular by far is this pair of mirrors, so-called KB mirrors, Kilpatrick-Bath mirrors, which is a pair of mirrors that work one after the other, focusing separately in the horizontal and the vertical direction, or opposite, doesn't matter. And often they are also bendable mirrors. What kind of incidence angle, what kind of material, all that depends on the energy we are working at. But the good thing about these guys is that they are largely achromatic, so we can use the same mirrors for a wide range of photon energies. They are difficult to manufacture if you want to go to the ultimate performance, but okay. So as you can see here, for example, the incidence as you go to higher and higher energies, for example, here for 6 kilo electron volts, the incidence has to be more grazing, which means you will need a longer mirror. So maybe you need a 3-meter mirror with a very high polishing, very good focusing, and so on. And sometimes you even want to change the radius of curvature of that mirror. So the mechanics is not trivial, but it's doable. And then only for completeness, I included this that work in normal incidence, but they are useful only for very, very low photon energy. So they're basically only used for nano ARPES beamlines, so for photo emission at low energy. And they work at fixed energy, but they're quite good. It's just for low energies. And by far the most used X-ray optics in microscopy, be it magnetic or not, is the zone plate, which is a refractive element. So it's alternating opaque and transparent regions to the X-rays, and it focuses by diffraction at a certain distance from the zone plate. And they work for many, I mean, they can cover many photon energy ranges. Of course, you don't need the same one for all the energies. You need, let's say you can work with the same one up to 1,200, then another one for up to 4,000 and so on. So you need several if you want to cover a lot of energies, because the same material that is opaque at 300 electron volts is not opaque at all at 3,000. And as you see here, it has increasing widths of the zones as we go towards the outer radius. And you can see already here what is the limiting factor with zone plane optics is that we need ideally zones that are very, 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 very narrow. But if we want them to be opaque, they need to be very, very, very tall, which means these are very fragile objects and very difficult to fabricate, okay? So what limits the resolution of a zone plate? There are several things. The main and foremost, let's say today, is this outer zone width. So it's the fabrication, it's a materials problem. Is so the width of the outer zone. What limits also is the ratio between the entrance and exit arm. Of course, if one could have an infinitely long beamline with several kilometers entrance arm and then have the sample very close to the zone plate, one would have a very large demagnification. This is not possible, obviously. And then also the chromaticity of the beam. So normally, nowadays, the zone plates are used in conjunction with a monochromator. So already in monochromatic beamlines. It can also be avoided, but the resolution will be limited by that. So what do we want? Again, a small source size, a long entrance arm and short exit arm, a monochromatic beam, and a small outer zone. The state of the art, let's say the best microscopes in the world operate in the 20, 30, 40 nanometers. And the world record published last November is 7 nanometers. So when this has been, you can imagine this is a challenge not only for fabricating the zone plate, but we are talking about a thermal and mechanical stability that is outstanding. You can see also the price that one has to pay to have this resolution. The focal length of this experiment is less than half a millimeter. So there is not many things that one can do to the sample to achieve this resolution. And also in this case, this was done in scanning transmission X-ray microscopy. You need to have a positioning and a position feedback system that is better than this 7 nanometer, considerably better, okay? So that it doesn't limit your spatial resolution. So you see in the design of a good microscope, it's not only the optics, it's many things that have to be taken into account. And of course, when one gets to this sort of world records, let's say, the transmission is maybe a few percent only. So one is losing more than 90% of the beam. And also the depth of focus is getting smaller and smaller. In this case, I think it was around 100 nanometers, which is not so bad. But if one wants to do tomography, 3D systems, and so on, it's already a killer. There are other ways to focus X-rays, and the only one I will show today is a capillary, which is a sort of mirror with a tube-like aspect. I will not go through all of this. Also very important for a microscope. We not only want to look at the sample, but we want to look at the sample as things happen to it. So always think about the sample environment. Can I apply fields? Can I vary the temperature? Can I measure the temperature? Can I put some gas in? Well, for Spintronics, the gas maybe is not important, but all the other things is. Electric pulses and so on. So here you see a few examples in different geometries. For example, for the PIM here in the upper left, it's very important that the sample region is clear and flat, but behind you can put many things. On the other hand, on the right, if you see the DXM, the center has to be completely free of anything, and the sample holder has to be very flat in this direction so that I can rotate to look at the sample with different angles. And in the STIXM, which is the lower left example, is the same. Yeah? The region of the sample has to be relatively flat, so I can come close with the optics, and so I can rotate at least a little bit to look at different magnetization components, so not only the normal components. So this is also something to take into account. So I will go first through the PIN microscopy, which is the type that is full field and is an electron microscopy. So one illuminates a sample with X-rays of a chosen energy and polarization, but then really one does the imaging with the electrons. So what one needs is electron optics. In this case, electromagnetic optics can be also just voltages, but normally it's electromagnets, or a combination of electrostatic and electromagnetic optics. What is the advantage of this with respect to working with X-rays? Well, depends on what you want to look at, but in the optics, let's say, if you have an electromagnetic lens, it's very easy to change its strength or even to turn it off, which is not the case with an X-ray mirror, let's say. So one can work in different modes, not only imaging, but this can be combined with diffraction modes, dispersive modes, and so on. So this is very good for epitaxial systems, for example, when the substrate cannot be transparent, for putting functional substrates, for example, piezoelectric substrates that we have been working with a lot to apply strain in situ or strain waves even. The images, the dichroic image is typically obtained, be it in PIM or be it in TIXM, by subtracting pixel-wise images acquired with opposite polarization or complementary polarization in the case of linear dichroism. So in this case, this is I think it's a very clear example. This is an image of small nano objects. Let's say they are like ovals, nanorods, let's say, that are oriented in two directions on a substrate. It's spermalloy, I think. And this is the direct image in absorption. So here one sees everything that has iron looks bright. These small nanoparticles have the magnetization along their long axis due to shape anisotropy. So if one does now the XMCD image, half of them seem to disappear because they have no magnetic contribution in the direction of the beam incidence. If one would rotate the sample 90 degrees, one would see the other half of the nanoparticles. Okay, I like this example because it's very clear. And the same here, if we have the typical closure domain in a square, and the beam incidence comes from the right here, then we would see white, the magnetization that is aligned parallel to the beam, black, the one that is anti-parallel, and gray, the perpendicular one. So thinking about the geometry is always important. The incidence, in fact, is not fully in plane, that doesn't exist, but it's grazing, in this case, 16 degrees. There are some beams where it goes up to 30, but 16 is quite common. And you see, in fact, we always see a combination of in-plane and out-of-plane contrast, and with different weight. So this permits distinguishing, for example, this kind of textures when one has out-of-plane, in-plane, out-of-plane, in-plane. So this is an example of a magnetic scheme. Can one obtain the full vector magnetization? Yes, well, combining images measured at different incidence angles for 2D systems, of course, not in depth because we are working with electrons. Electrons don't escape from very far in the bulk. So this is an extremely surface sensitive technique. We can do images of things of a few nanometers depth. Yeah. And antiferromagnets also. This is one of the cases where it's important to do element selective imaging. For example, these are, let's say, cobalt monoxide or doped with nickel cobalt monoxide islands, microstructures. And here one can see, for example, that the domains on the cobalt edge, the domains and the nickel edge are the same, so they of magnetic origin, and they are the same, whereas the ones on the oxygen edge are different. This means that in one case we are looking at magnetic domains, and in the other we are looking at structural domains, which also give rise to linear dichroism or natural dichroism, as one wants to. One can call it also like that. So this is just to make the point that one of the very important class of systems that can be very well measured by element selective techniques and not otherwise is the systems where the magnetic moment, the overall magnetic moment or the magnetic field or the stray field is very small. So either zero because it's fully compensated, or very small because it's a ferrimagnet. In this case, one can look at only one component, if it's a compound ferrimagnet or a synthetic antiferromagnet, and one can see Even, for example, if one has a synthetic antiferromagnet system where two layers look like this, they are of the same material, still in PIM, we are more sensitive to the upper layer, so we will see some magnetic texture, even if they are fully compensated. And this is something that can only be done with this extreme surface sensitivity. It cannot be done in transmission. Okay, so all in all, I think I have said all of this. It also has drawbacks, of course. The samples are at high voltage, they have to be in ultra high vacuum, they have to be conductive, relatively flat, and we are imaging with electrons. So the fields that we can apply without distortion is very limited, are very limited. In transmission, we cannot work with an opaque system, we have to work with a transparent substrate, transparent to X-rays. Okay, this in particular, this is the setup in the TXM at ALBA. This is let's say the focusing lens is a condenser, and the objective lens is a zone plate, as I have shown before. And the sample is also in a rotation, a high precision rotation state specific for tomography. It was not designed for magnetic tomography, it was designed for biology, for cryotomography of cells, but we have been using it for magnetism also. So the kind of substrates that one can use either electron microscopy type grids or silicon nitride membranes, or for freestanding systems. Now there are many groups working on three-dimensional objects in magnetism to see the effect, for example, of the curvature on the magnetic interactions, geometrically induced DMI or geometrically modulated and so on. So one can use this kind of just half moon holders where the structures are freestanding. This microscope has 26 nanometer resolution in 2D and around 50 in 3D. And what it looks like in reality is something like this, more or less. So the shiny central cylinder is the cryo shield. On the right, one can see the holder of the zone plate, which during operation actually is much closer to the sample, is around 1.5 millimeters from the sample. On the left, one can see the capillary condenser that also during operation is much closer, is around here. And okay, and the rest is not important for us right now. As I said, just like in PIM here, if we just go through the sample in normal incidence, we are just being sensitive to the perpendicular magnetization, perpendicular to the substrate plane, let's say. If one wants to look at more components, one has to rotate, which is absolutely not a problem, but it's more images, okay? And this is the way to look, for example, to separate the out of plane and in plane magnetization in this kind of multi-layers, and look at buried magnetic singularities and look at the in-plane component and so on. So these are looking at samples that are in all, I think, 300 nanometers thick. So the thickness limit for this kind of photon energies, so for soft X-rays, is around here, 300, 400 nanometers maximum. If one wants to obtain all three components of the magnetization in a 3D object, so with lower and lower symmetry, one has to do not only one rotation axis, but two rotation axes. So first look like this, rotate the sample, and look again at 90 degrees if possible, if the geometry permits, okay? This has been done both in hard X-rays. Here the geometry does not permit 90 degrees rotation, but 30, but that's already enough. This was demonstrated the first time for hard X-rays in 2017, and for soft X-rays right after that at ALBA. And well, as you can see, one obtains a large amount of equations, but it's solvable, let's say, with some effort. Why go to hard X-rays or why go to soft X-rays? Well, hard X-rays permit going through more amount of material. So if you want to look at an object that is a few micron thick, there is no other choice but to go to hard X-rays. On the other hand, the part of the scattering that is, or let's say the dichroic component of absorption is much, much stronger for soft X-rays. So if you can do it with soft X-rays, do it with soft X-rays. The resolution is better, and the magnetic component is much larger. So you see here, for example, for transition metals, the amplitude, let's say the ratio between so it's 1 order of magnitude more dichroism in soft X-rays than in hard X-rays. No, 1 order, no, it's much more. And even in hard X-rays, one can look, for example, gadolinium, samarium, so some rare earths one can look at, but still it's okay. It would be much better to look in soft X-rays if one has a sample that is not so super thick. Okay, but this is also a consideration to think about when going to do an experiment. So the advantages of this I have already said. In this case, for example, external magnetic or electric fields do not perturb the imaging because photons just ignore them. Disadvantages, one cannot look at such small amounts as with PIM. For example, in PIM, one could have a magnetic image of an amount of material that is less than an atomic layer if it is on the surface. And here we need, let's say, 1 or 2 nanometers. And one needs to put the sample on a transparent substrate, which has sometimes is not easy. If you do molecular beam epitaxy, you will not be able to do it on a silicon nitride membrane just because I asked you to. Okay. And another disadvantage could be that the imaging resolution depends on the mechanical stability. So heating the sample and cooling the sample is not a fast process. So one will need to realign the optics at each stage. One can go then in a similar setup, so also looking in transmission, but in a scanning way, as I said in the beginning. In that case, one needs the zone plate before the sample, and then also what is called the order selecting aperture, which is just a pinhole to illuminate a very small region. Very small, meaning 100 nanometers, 50 nanometers, 20 nanometers of this order. And then one can choose what detector to use, either a point detector in transmission or an electron detector, fluorescence detector on the other side, and so on. So this one, this geometry is particularly good for spectrum microscopy. For example, it's much faster for spectrum microscopy because one can choose to do spectrum microscopy only at certain points and not always of all the area. The optics is simpler. Of course, the mechanics is more complicated, but and since one uses a point detector, one can use the fastest detectors in the market, which are avalanche photodiodes, which means with these detectors, one can go sub-pulse resolution. So not only looking at, so one wouldn't need to change the delay between the pump and the probe for each slice that one wants to look at, but one can do discrimination, electronic discrimination of the different slices within these 2 nanoseconds. So this is for the let's say for the ultimate time resolution. This is an advantage. Disadvantage, well, to make an image takes longer, of course. The electronics is more complex, and the mechanics is more complex. Just the last few minutes, the more advanced imaging approaches, the so-called lensless imaging approaches, which are not really lensless, you will see, but they have less lenses, that is true. For example, in holograph, so based on diffraction and which need a coherent source. If the source is not very coherent, what one does is use a pinhole or let's say some sort of slits to limit and use only the central part of the beam that is more coherent. With new generation sources, the amount of coherent flux will increase and increase, and this type of imaging will have more and more weight. The first example of magnetic holography or dichroic holography, let's say, was demonstrated in 2004. And in this, it's just like optical holography. Eh? One has one part of the beam that goes through the sample that has to be on a transparent substrate. So it's a transmission technique. And another part of the beam that then interferes with it goes through a reference hole or reference pinhole. And this is what is limiting today the resolution of the technique, okay? This is similar to the approaches in TX and let's say 20, 30 nanometers, more or less. Although there are experiments where, although the pixel size, let's say, is 40 or 50 nanometers even, one can track the position on an object with higher resolution. And in this case, for example, this was done, if I am not mistaken, no, I don't want to commit. I'm not sure if it was done in SLS or in Slack, but it's here the resolution is 40 nanometers, but the results show that the tracking of a particular skyrmion, of the center of the skyrmion, is better than 5 nanometers, okay? And with this, they could excite the skyrmion and follow its trajectory as a sort of vortex motion. The next generation, which is really almost lensless, is Tychography, which has been around for 10 years, more or less now, dichroic tychography, which is a bit hard to understand and even harder to explain. But let's say that it's a scanning technique, okay? And it permits reducing the resolution from the spot size to a few times below the spot size by over-defining. So let's say one would do a scanning, diffraction imaging in a scanning manner with overlap of the different regions and use these overlapping regions as a sort of the reference in holography. It's a bit hard to understand, but instead of having a reference hole, the sample is its own reference, the neighbor region, let's say. So it has a quite convolved, let's say, algorithm, but is giving the best spatial resolution so far. It is not fast. It is not fast to measure because, as you see, it's a scanning technique, and not only scanning, but scanning with overlap. But it permits, for example, going sub 10 nanometer resolution in 2 dimensions. I wouldn't use this to go to the 3rd dimension because it's really slow. But okay, with the next generation of sources with higher coherent flux, this will get even better and better. Can only get better. The world record resolution nowadays is 45 nanometers in hard X-rays and 12 in soft. I think this 12 nanometer in soft, if it has not been beaten, it will be beaten very soon. And one thing that one can see here is if you see the best resolution with hard X-rays in non-magnetic imaging is 14 nanometers. So we go 3 times worse when going magnetic. Why is this? Because we are limited by the cross-section of the dichroism in hard X-rays. Whereas in soft X-rays, there is a difference, but it's not so bad. In summary, so as an experimentalist, I would like to tell you to always choose the right tools for your problem. It's very important to use the right instruments. And in the case of magnetic microscopy, you have to ask many questions, like what is my sample geometry, thickness, material? Is it radiation sensitive? Can I have it for days and days until the beam to get the best resolution in all dimensions, in all the voxels, or will it decay after 2 hours? Do I need 2D or 3D magnetic information? Now, meaning is it a layer or is it a thick sample? What kind of spatial resolution do I need? Do I need the full vector magnetization? Do I need to rotate, or do I need just one component to understand my problem? Do I need, what kind of timescales do I need? Do I want to look at the magnetic landscape as it is static, or do I need to apply different fields or other impulses? Do I need to correlate these results with other imaging techniques or with other non-imaging techniques? So all this, do I need to do spectroscopy or only microscopy? So all this are things you have to ask yourself, not only for Spintronics and Synchrotron, but whenever you're going to do an experiment, let's say. This is one important message. The other important message is don't overdo it. So you might need a synchrotron, but you might not need it. And there are many magnetic imaging techniques around, like MFM, spin polarized STM, MOC microscopy that might be perfectly suited to your challenge. So just, and in case of doubt, the third important message that I would like you to remember is ask, please ask. We are nice, normal people that work at the synchrotrons, and synchrotrons are paid with everybody's taxes. So it is, in fact, our job to help you design your experiment. And with this, I will finish and welcome your questions.
Great. Thank you very much, Lucia. It was a great talk. I think it was different to what we have heard so far, and that's what I think it's interesting. So let me have a question first. This is my question, because so we've heard in the past talk with Andy about oscillations and, let's say, magnetization dynamics. So my question is, like, what is could you just comment a bit on the state of the art on the, let's say, fast or ultra fast techniques in synchrotron? Because there's an interest. We'll hear talks about antiferromagnetic spintronics and antiferromagnetic oscillators. So can we go to femtosecond with X-rays? This is the question. Or how is affected? You mentioned it, basically 3 techniques. Can all be used with femtosecond pulses? Or what do we need to do?
You need a strongly interacting sample that survives a lot of photons. To femtosecond, you will need to go to an XFEL or to femtoslicing, which is available in very few synchrotrons. I would go to an XFEL rather. I would go to almost single, so not scanning, but almost single shot experiments, so small samples. Let's say. And transmission for sure. Transmission and coherent diffraction imaging, I think, yes. To go sub-spot resolution. I don't know what is the world record right now. It's the XFEL pulses are, I don't know, in Hamburg, 100 femto, something like that. There is also, for antiferromagnets, there is an interesting source, which is not exactly a synchrotron, but there is a terahertz source in Dresden, the ALBA facility, which could be interesting, but I have never been there, so I have no idea of the characteristics of the beam or anything. But terahertz at the synchrotron is not available as far as I know.
So then what will be the available time scale at, let's say, at the normal synchrotron? So people can know all these techniques, at what time scale can be used in most of the synchrotrons?
In most of the synchrotrons, I would say the resolution, the standard time resolution is in the tens of picoseconds. Another thing is that you can excite things with much faster, like, I don't know, few gigahertz.
Okay.
That's more or less what is available. You have to think, at some point, if you want to go to excite a sample with many gigahertz, you need such cables. Imagine scanning that, or keeping it from having any torque when you want to rotate.
Okay, that's true, but we've seen that you can excite gigahertz dynamics in gigahertz dynamics with DC current. So it could, you can get in spin transfer torque oscillators. Okay, so let's see, there are a few questions. So the first one from Fernandez Roldan is saying, thank you for the nice talk. And could you please tell us a little bit more about time resolve techniques and their resolutions for domain wall dynamics, pros and cons? So it's similar, but
pros and, the fastest that you can go is with an avalanche photodiode. In a STIXM, but it's single, but it's, I mean, it's fast. Let's say getting a single point, it's super slow. You might need 3 days to get an image of the whole sample, but you can look at spin waves in, I don't know, even in nanowires, it has been done or it's being done, or on edges of structures and this kind of thing. This is a synchrotron. Then there are X-FELs, which are another league, let's say. And I don't understand what he means by advantages or disadvantages. If you need it, you need it. If you don't need it, don't look for it. It's much easier to measure static.
Sure. Okay, one more from Marina Ferreira. She also thank you for the lecture. And the question is, are the PIM and STIXM experimental setups compatible with low temperature measurements? And if so, what temperatures can be reached?
Let's say the lowest temperature that I know in a PIM is 40 Kelvin. Much lower is tough. I mean, there is a project to do a low temp, to do a few Kelvin setup in Leiden University, but it's not in a synchrotron. It's for LEM, it's for low energy electron microscopy, but the microscope is very similar. But to go towards this, you already have to cool the whole objective lens, which is massive. So in PIM, the objective lens is a couple of millimeters from the sample, as you know very well, and it is very massive. So you need to cool that also. At a synchrotron, I know of 40, maybe 30 degrees, 30 Kelvin. And STIXM, I know about 60, but I don't think cooler, but there is nothing fundamental. Well, it's not easy to combine with the scanning. But there is nothing fundamental. There is nothing fundamental against going to 20. I mean, maybe millikelvin is not possible because you need all the shielding and all. So you think that to get very good resolution, you always need to get to approach the sample with the optics quite a bit. But tens of Kelvin, yes.
Should be possible, I see. So one more question from Fernando Bartolome. He also thanks you for the nice talk. And you're an expert on XPIM. So the question is, what about the magnetic fields that you can apply in XPIM experiments? I mean, what are the limits? What happens when you apply a field? And also differences with in plane, out of plane?
Well, out of plane is a bit better because the electrons, let's say, rotate and defocus, but they don't go to the neighbor beamline, let's say. But a few tens of millitesla is, I would say, the limit, even for out of plane. And for in plane, so for out of plane, maybe you can go to 40 millitesla, and for in plane, maybe half of that. What happens is that at every, well, you are losing resolution for sure. And at each stage, you have to realign several lenses to keep looking at the same object and to keep having, to still have the electron beam go through the apertures that it has to go to have good resolution. So not only so you have to adjust, let's say 3 or 4 aligners and stigmators to understand what you're seeing, not to have the same resolution as without any field.
Yes. Okay, well, thank you, Lucía. So I see no more questions. So I think that now I have to thank you once more. I cannot clap, but and I think that with this we come to the end of this session.